How to change?
Should see it. And thank you everyone for joining. We are getting set up as we speak.
Mm-hmm. Perfect. Yeah.
Great. And can you see my screen okay?
Yes. Um, is it possible to move the second slide to the last? I mean, the last one. I mean, move the yes. Because first of all, we'll introduce the IEEE. I mean, the board, and then yeah, this is the first, and the next will be the intro about the board. Yeah, the second one. And the third is all these, yeah, the logos, and then next is the speaker. Is it possible to
Yep. Yeah, so I'm gonna
change,
leave this
yeah,
up now
the
until we get,
sequence?
yeah.
Hmm.
So you want to do
This one, yeah, the first,
one,
and then
two,
second,
and then the other.
uh, one, and then no, this one is the last one.
Yep,
Yeah.
right.
Hmm.
Okay. So I'm just gonna leave this up now just so people know what they're joining, if that's okay.
Hmm. Yeah. Then I will introduce DMR, and then during the Q&A session, Gerhard will join. Then
Yep.
he will chair the session. Yeah.
Okay. Just need him to join.
Right now we have how many? Five
Three.
participants.
Three plus
Mhm.
us. Yep.
The participants, the number, does it include hours? I mean,
So what I see from
oh,
my
three
end is
attendees. Okay, yes, I see. Yeah,
right.
attendees three, and then okay. Yeah, has not joined it yet.
No. Yeah, I just
Good.
sent him a message.
Mhm.
I hope the time zone didn't
Yeah, exactly. I'm afraid
problems.
the time zone.
Good afternoon.
Karen,
Everyone,
Henry, can you hear me?
we
Ah,
can.
yes. Hey, good
Perfect.
afternoon. Yeah, yeah. Thank you for
So
joining.
here's my video.
Yeah.
All right. So we'll give folks a few minutes to join
Hmm.
with WebEx being a challenge, I'm sure.
Yes.
So, presentation is ready.
Great.
Hmm.
That's a good thing. So quiet.
Hmm.
Yeah, and we only have 8 attendees right now.
Yeah.
Right now, 8 attendees. Yeah.
One of them is there twice, so
Yeah. Yeah, that's why I'm thinking there was a problem dialing in or something.
Yeah, people are joining now.
Yeah.
12.
Great. Let's give them a few more minutes. I
Yeah.
sent a few reminders. So
yeah. So are we visible already?
yes, we are.
Hmm.
So I will leave it up to you, Henry. When do you want to begin?
Yes.
Do you want to give it a few
Yeah, I
more
will
minutes?
start. Okay, maybe 9:03 or now 5. Yeah. Yeah, let's
Okay.
see.
All right.
Hmm.
Perfect.
Okay, maybe on the title slide you can change the 9 a.m. EST to EDT.
Um,
EDT. Yeah, EDT.
how about just that?
Or just ET.
Hmm. That's okay. I'm just gonna check my email, make sure there's no problems going on. Thank you to everyone who's joined the call. We're going to give it a few more minutes to allow additional attendees to dial in, and then we'll get started. Thank you for being on time.
It looks like we got one question.
The chat room? Oh,
There is one raised hand.
okay. Yep. Oh, you see it? Where? I don't see the question. Only to you only, right?
I see in the attendance list there is one participant who has raised the hand.
Yeah. Hi, Sarah. This is Karen Panula from IEEE. I see you have your hand raised. Do you have a question?
Mm-hmm.
I unmuted you if you do.
Okay.
Okay.
And then maybe we can start now.
Yep. Hang on one sec. Let me
Okay.
just hit the record button. Give me a second.
Okay. Okay, then I can start now, right, Karen?
Yes, please. Yes, please.
Okay. Good morning, good afternoon, and good evening, everybody. This is Henry, a member of the IEEE IoT Activities Board. On behalf of the board, welcome all of you to join today's webinar. The Internet of Things, IoT, is one of the most exciting technological developments in the world today. The key missions of the board is to promote IoT. Currently, we have 12 IEEE societies. With their support, we have this webinar series. Each month, we have an exciting IoT topic. Today is the fourth one. We are very delighted to have Dr. Diama Bratna to deliver an interesting topic related to industrial real-time communication from sensors to cloud. And Dr. Geha Engel will be the moderator in the Q&A session. I hope you can all enjoy this webinar. Should you have any question, do feel free to type your questions in the chat box. Before the start of the webinar, I would like to introduce Dr. Bratna. Dr. Diama Bratna is with B&R Industrial Automation since 2013, where he is a unit manager in the R&D department system software. He is responsible for the development of a wide range of industrial connectivity solutions based on real-time Ethernet and of real-time operating system automation runtime for PC and PLC platforms. And before B&R, he worked as a university assistant, that is assistant professor at the Institute of Computer Technology of the Vienna University of Technology, areas of field bus building automation and artificial intelligence. He studied electrical engineering, where he obtained a Master of Science in 2004 and a PhD in 2007, and passed both degrees with distinction. Oh, excellent. Dr. Bratna is a senior member of IEEE and an IEEE IES ECOM member. He published more than 70 reviewed scientific publications and more than 100 scientific publications in total, as well as 5 international patents, and edited the IEEE 61158 standards. He is actively involved in organizing international conferences, editing high-ranked international journals, AEs of TII, TIE, and IEM, and drafting international standards in the IEEE and OPC Foundation. Oh, very impressive bio. Yeah. Okay, then I would like to pass the time to Dr. Brunner for your webinar. Thank you. Thank you very much. Yeah.
Okay, thank you, Henry, for the kind introduction. Also from my side, good morning, good afternoon, good evening to everybody. While I'm talking, I'm trying to share my screen. So you should be able to see my slide now. Okay, and I think I can also stop the video. Let's see if I can do this here. So that everybody can concentrate on the slides. So the talk that I have prepared for today is about industrial real-time communication, and the aspiration of this communication technology is really to be applicable for all types of industrial automation communication requirements, from the sensor level up to the cloud in converged networks, whereby converged network means that there is a common understanding of real-time requirements and that different protocols can also share the same communication network. And in particular, the communication technology I'm talking about today is composed of OPC-UA on the one side for data description and IEEE TSN on the other side for the network infrastructure. Before I go into details, I would like to emphasize that the viewpoint that you will recognize during my talk is the viewpoint of a company that's engaged in machine and factory automation. So you roughly see the revenue distribution of my employer here. We're doing PLC systems, drives, and industrial PCs, roughly 1/3 each. So that's the main markets we are at, and that means we are more on the automation pyramid on the lower end, like in the field devices and in controller-to-controller communication. If there are any questions, you can raise them today in the Q&A panel, as has been already said, but you can also contact me directly. You see here the contact details for later if you want. So if we talk about real-time applications in a production environment, what is meant? So usually if you think about the production plant, you'll have different machines. Each of these individual machines has a different task or a different part to produce. Those machines usually are connected in so-called cells, where the cells together then produce more complex parts and do the control of the different machines, and that cells themselves are then combined into lines. So in a production line, you have then the entire production of a complete product. And if we have a look into those constructs from a communication and from an electronics point of view, then we will see the devices that are in those machines and cells and lines. Those are typical industrial devices like drives, like PLCs, PCs, like I/O boxes, and all of those devices are interconnected, which is depicted here with this switch symbol. And obviously, all of those are then together connected in the factory network or in the plant network that's required to let those devices communicate. Regarding real-time requirements, the highest real-time requirements we have are on the machine level. And if we go higher in this hierarchy, then the real-time requirements get relaxed. And for the lower end here, TSN, which I will introduce then later, fulfills these requirements, so provides an infrastructure for that communication. And obviously, if it provides it for the lower layers, then it's also more than good enough for the higher layers. But there is also other technology. It's called DetNet. I just want to make you aware that there is what's done with TSN on layer 2 Ethernet. There is also an effort on standardizing real-time communication on the IP layer of the ISO-OSI model. But TSN is further advanced, and this is what this talk also focuses on today. Okay, so how is today's situation in production machines or in the production environment? Today we have, you see here, this so-called automation pyramid, where you have on the bottom layer, you have the field devices, then you have the controllers, and then you have several types of management systems. And on each of these lower layers, you have competing technologies on the market. So I have put some of the logos of the different technologies here on the slide. Currently, in a real life plant, you will see many of those, if not all, and if not more, than are here on the slide. And they are not interoperable, so you can't directly exchange data. They have a different understanding of real-time requirements. They have a different understanding of non-real-time requirements, and you simply can't put devices that are certified for one of those technologies into a network of another of those technologies. This is one challenge that we face in production environments. The second challenge is where also this initiative is concerned with IoT challenges. So more and more producing companies have the challenge to compare their machines, for instance, to do some artificial intelligence with data that's gathered from the production environment, to store running data. And with those different data representations on the lower level, this is currently a very tedious and complicated task. And just one aspect of it, security, for instance, is not really tackled in the existing Ethernet-based field buses at all. And there is another requirement that's challenging today, which is the complexity in the electronic systems in production environments is increasing. Typical machines like 10 years ago, they had, for instance, let's say 10 motors and 10 servo drives. And today's machines, a similar machine today may already have like 30 motors and 30 servo drives, and also the amount of IOs and the amount of things that are controlled in a machine is increasing a lot. Also, the variants of the different machines are increasing because of customization of products. So the requirements on variability and also on the amount of devices is ever increasing, and field bus systems that are based on 100 megabit sometimes cannot deal with that requirement in individual networks. So you have to create networks of networks, and it's getting more and more complex with the existing technologies. And that's that conclusion is not entirely new. So several years ago already, an initiative with a lot of production or a lot of system providers from the automation market have created an initiative to standardize a new technology. And this new technology consists of OPC-UA over TSN networks. And as already indicated a bit, OPC-UA is the portion that's responsible for data description and data exchange. It brings security, it brings semantics, and it brings self-description capability into data that's being communicated. So it's more of a kind of object-oriented approach rather than the traditional approach in the field bus systems. And TSN, on the other side, provides a network infrastructure where you can reserve guarantees for deterministic communication. Those two technologies are distinct. They have different origins. They have different standardization groups. But for the industrial automation market that I'm talking about today, those two technologies make most sense if they are used together. That's why also this term OPC-UA over TSN, or later I will talk about OPC-UA FX, is coined. And when I talk about those technologies, I always mean both of them together. So regarding history and standardization, what you see here is the OPC Foundation has founded the so-called Field Level Communication Initiative. And this initiative has been presented pretty accurately 3 years ago at the SPS IPC Drives Fair in Nuremberg in Germany. And if you look at the logos here of the system providers, you see that a large majority of device providers and PLC providers is taking part in this initiative. And I've copied here the mission statement of this initiative, which says the goal is an open, unified, standard-based industrial IoT communication solution between sensors, actuators, controllers, and cloud, addressing all requirements of industrial automation. So really applicable for all kind of machine automation, factory automation, process automation, and so on. If you are interested in what's the current status and what's been done there, I have copied here the link to the introduction on the site of the OPC Foundation. And we are heavily involved in finalizing the standards. And the first release of this standard is planned for end of this year. So we are currently in the last few weeks of preparing the release candidates for review. And the release is planned for end of this year. And in very short words, what's the value of OPC-UA FX? So FX stands for field exchange. That's the name of the technology that's in the standards. It's really to have not this automation pyramid with the fragmented networks and with the gateways between them and with the individual management and so on and so forth, but to really be able to provide one communication infrastructure with flat networks and with communication relations as needed and with a similar understanding of the data that's being exchanged. So that's the real benefit that this UAFX technology will bring. Few words about performance, because if we talk about real-time communication, the performance of the network is very often of concern. So in preparing for this standardization, we made a deep analysis of the reachable performance. And what you see here on the right in this diagram is theoretical analysis dependent on the number of network nodes and dependent on the payload that you have in the network compared to some of the existing technologies in the market and what you can reach with OPC-UA FX on gigabit physics. And in average, you can see the other technologies, they perform relatively similar. So there is a factor of roughly 18 that you can increase either in terms of exchanging more data or having more devices or having shorter cycle times. That's then whatever the application needs. And if you're interested also in this analysis, then I have put here the reference to some paper that we have published with the analysis. Before going into technical details, how this looks like, I think in a webinar like this, it's also sensible to give a bit of practical example where the technology is used and what's the current status. So I have 4 examples here that I would like to share with you of production machines. The first example is a blow film machine that creates plastic tubes. And you see from these images, it's a quite large machine. And for this particular company, it consists of 3 modules. And those 3 modules, they are produced in 3 different locations with individual history and with individual suppliers. And they also use different communication technologies inside that modules. And in the end, if the entire machine is constructed, then they have to introduce gateways and they have to collect data from the different modules in various ways in order to control the entire machine. And this is a pretty standard case for larger production machines, how they are produced and assembled today. Another example is this machine here. It's called a side loader of medical products. So on the left side here, you see the final blisters containing the medical items, the pills, is coming here on the left side, and then it's packed into the paper boxes, and those paper boxes, they are then lasered and they are glued, and all the glue points are checked. So, and the challenge here is also, it's quite complicated communication requirements. You have 7 PLCs inside the machine controlling different aspects, and lots of reconfiguration requirements. So that there are not enough pills from one kind to produce for a long time. So this machine, the challenge here is that this machine needs reconfiguration at least twice per day, and also some of the tools of this machine are exchanged twice per day. And this needs to be really fast, and this needs to be also controlled from other systems. Another example where we talk again about performance is in the textile machinery. You see one of these machines that spins cotton fiber, and those can be pretty large. So on the right side, you see one of these machines. I think this box here on the right side is like 4 meters high. So it's probably 50 or 70 meters long, and it contains up to 500 axes on each side. And currently it's composed of a lot of subnetworks, and the promise with TSN and gigabit physics would be to reduce the amount of networks and hopefully being able to control one of the sides of this machine in one single network. Another example here is gas engines. So we are here in the 1 megawatt or larger region for those gas engines. And also here it's the case, parts of this machine are produced on different subsidiaries with different technologies, and then they have to be connected. And also the customers have different expectations from the communication interfaces. So what this supplier is doing, he provides 8 communication technologies as interfaces to exchange the internal data of the machine. And obviously on the PLC side, it's a lot of effort maintaining these technologies, transferring data from one to another and making that available. And I could extend on this list rather lengthy, but I think you get the general point that having these different types of technologies and these different types of data management is a very challenging situation in the production industry today. Okay, now I would like to go a little bit into the technology on the TSN side and also on the OPC OA side. And I would like to start with TSN. So first of all, why do we need TSN, or why do we need a rather capable or rather complex network infrastructure? In the beginning of the standardization efforts, there was an effort to work on real-time and non-real-time requirements for communication. And it got evident rather soon that the different industrial field buses that we have today have a different understanding of real-time communication. They have a different understanding of hard real-time, soft real-time, and also other types of communication. And we formalized that, and in the FLC initiative, we came to a classification of different traffic types that are needed in industrial automation. And we found that we need 8 different traffic types to be able to bring over what's happening today in industrial automation in the different field buses into a converged network so that the different devices can operate in a similar manner as they are doing today. And as I will show a bit later, TSN allows to run the different traffic types as they are defined here with individual guarantees in one network and in one infrastructure, and apply guarantees to the different traffic types. For instance, guarantees for deadline of communication, guarantees for latency of a frame in the network, also guarantees for bandwidth and so on. And those can be individually maintained for these different traffic types. And what has been also considered for brownfield installations, so where existing installations are being extended with TSN infrastructure, we also made an effort to make a transformation to be able to carry brownfield traffic in individual traffic types on TSN networks. So that's also possible with TSN to have this extendability from existing installations. And that's basically the motivation why to go in such a admittedly complicated technology as a network infrastructure for industrial automation. So to give you a bit more of a background, what is TSN actually when we talk about, so the acronym TSN stands for Time Sensitive Networking, and the Time Sensitive Networking Working Group is a working group of the IEEE in the 802.1 group. And all the standards that this group produces are then coined TSN standards. And just a few seconds, I will put on the large picture before going a little bit into details. So the standardization work that's done in this TSN group is first of all around profiles. So it has been identified that different application areas have different needs, and this is represented in those profiles. And here in the middle of this slide, you see the industrial automation profile. It's the 6802 working group. And this working group selects among the other standards that are on the bottom of this slide, which are the relevant ones for this market. And the different standards here, they are a bit grouped now according to the goal that they're pursuing. So those standards are created around the areas of time synchronization, to have a distributed time base among the different devices. Then there is a couple of standards that deals with implementing bounded latency on the network. Then we have standards around reliability. So now you should be able to see it better, around reliability, and then also around resource management. And I won't go into detail of all those 4 areas. You can see if we go to the left here, there are multiple mechanisms that have been specified to guarantee bounded latency. And there is also a lot of work put into resource management and configuration of those various parameters. And so this is basically on one slide. That's also published by the 802.1 working group. That's what TSN is about. So not all of those mechanisms for bounded latency can also guarantee very low bounded latency. So for the hard real-time requirements for servo drives, for instance, we talk about communication cycle times between a PLC and a drive in the range of sub-milliseconds. So 500 microseconds is a typical value, but also 250, 125 and lower values are already very typical values for communication cycles. And not all of those TSN standards can guarantee such low values. But there are still a few options. And just to show you a little bit on the discussions that we had on selecting among TSN mechanisms, I tried to make some depictions on how frame propagation in the network could look like using different of those standards. So for instance, there is this isochronous traffic type that you have seen on the slide before, which is the one that's used for the hard real-time requirements. And the option that I'm introducing now uses the QBV standard, which is also called scheduled traffic, and it uses time synchronization between the different devices for exchanging data. What you see here is a time-space diagram of a daisy chain topology, a very simple one. You have one PLC, and then in one line, you have 7 devices connected, and each of these devices sends one frame to the PLC. And with this type of technology, the first device will send at the beginning of the cycle its frame to the PLC. Then the second device will send it in a way that's propagated from the other device directly after the other frame. And that's how that so-called staple of frames or of packets is composed. And the sending times, they are calculated in a way that on the PLC side, the frames are received in a packed form. And that's the lowest achievable cycle time for this type of communication that you can achieve actually. These brown frames are the cyclically exchanged data, and then in the remainder of the bandwidth, in the white area, there is also free space for exchanging non-isochronous packets, and those blue ones, those are the non-isochronous ones, and this is just examples how it would look like if also that kind of packets are sent. Yeah, there is an analysis of reachable cycle times, and just to highlight the technologies that we are using, we have a distributed common time base that's required for the forwarding of the frames and also for the sending of the frames. And we have this time gating mechanism that comes with QBV, where each of the TSN switches will open a time window for different types of traffic. And you see here, this is the gates that are required for this isochronous traffic. And all the rest, which is now here depicted, can be used for other types of traffic. So this way here is a very efficient use of the bandwidth in the network. However, there are also other ways. So if you have real-time communication, but not with that hard requirements on reachable cycle times, then you can do a trade-off between less hardware implementation and also less configuration effort. And that's what this cyclic traffic type actually allows you. So we don't have cut-through forwarding, and we don't have individual sending times. So what's happening here is that the forwarding, since it's not cut through, but it's a store and forward forwarding, it takes longer in the switches, and also all devices will send their packets at the start of the cycle. And what you see here, this is the typical behavior of store and forwarding. So larger frames, they need longer times for being forwarded, and the shorter frames, they actually run into those larger ones, then they are queued from the switch and are released afterwards. And what you see here on the PLC side, the cycle times that you can reach with this approach are certainly higher, but configuration-wise, this type of network is much simpler to configure. Again, we have the common time base. We have also these gates, again, for this traffic type. And we have then the remaining bandwidth for non-real-time traffic. However, for simplicity in this type, you could also simply have common gating events for all that devices. And in reality, the time that you have here at the end of the cycle is usually much higher than in this figure. So that's also a very usable option, and simplifies this type of network a lot. Okay, then coming to a third option, not using time synchronization and not using scheduled traffic. This version is based on using preemption. And what you see here, if you don't have time synchronization, and if you configure sending times for your frames, then over time, those sending times, they will undergo this fading effect. So you can't really say at the common observer when the frames are really sent, because all these devices have their local time. But just to go through one example, how this would look like, I'm just opening this now. So all the frames are sent, and what preemption is doing, if a higher priority frame is sent and should be sent on an egress port where a lower priority frame is already sent, then this lower priority frame will be preempted. The higher priority frame will be sent, and on the next switch, on the next network infrastructure device, that frame will be reconciliated. So that's what you see here. So just those 3 slides were just to give you an overview on what the discussions are on how to use TSN for industrial automation. So coming to a conclusion, what will be standardized, or what will be published, how we use it. We are using in one of those standards that are going to release. We are using scheduled traffic, and how we are using it. For example, we are thinking about defining a default schedule that could look like this. On the circle that you see here, you have the different traffic types, and you have the progression of time in the circle, and one circle represents one communication cycle, and we have individual time slots for the individual traffic types. So for the hard real-time traffic, for isochronous, we have exclusive time slots. For the cyclic traffic type, we also have exclusive time slots. Then we have another time slot for even lower requirements, but still real-time traffic on the network. So you see here, those 3 ones are spread around the cycle for real-time communication. And then we also have other time slots where prioritized, we have the other traffic types for network configuration, for event-based control, for configuration, and for best effort. And all of those 3 have individual guarantees where they have highest priority so that there is no starving. So this is just an example of practical use of TSN for such a network infrastructure. Okay, with that, I would like also to give a short introduction about OPC UA, so on the data side. If we look again into this production environment and into the devices in this production environment, if you're using OPC UA, then what will happen, each of the devices will have their OPC UA server, and that OPC UA server exposes to the outside a representation of the data of this device. And yeah, in a network, you can then have a flat network of devices, all with these OPC UA servers representing the data. And so what's the value of OPC UA, or how does OPC UA describe the data? Compared to previous field buses, in previous field buses, you have the binary data that's been exchanged between the devices. And in order to understand that binary data, you have to go into the manuals, into the data sheets, and see, okay, bit 7 to bit 12 is this data point in this encoding, so I can understand this in this and that way. With OPC UA, it's a bit different. So you have the information model, and in the information model, all the data items, they have their data type and they have their data description. So you can really look into the information model and see, okay, this portion of the data is an object, this portion of the data is a variable, this here is a method, this could be an event, and so on and so forth. And you can really look into it and observe live the values and also the metadata associated with that. And even further, there are so-called companion specifications, where for different markets or different applications, some of those objects and variables and so forth, they are already specified with a distinct name and a distinct behavior. So you could, if for instance, one of those companion specifications would be applied in such a scenario, you could really look into, okay, this is a robot and this is a variable about the tool, and the method that's called has a name like welding or drilling, and you can have status information, and that's really self-descriptive and very intuitive to understand what's being exchanged on the data side here. Having a bit of a deeper look on such an information model. So here in the middle, for instance, you see a very simple information model from a digital output module. You have some configuration data, some status data, and then the individual data points. And if you then go deeper, you see also here on the right side the different meta information about these actual data points. You have the value, you have timestamps, you have user access modules, and so on and so forth. And this is everything standardized in OPC UA already for a long time. Yeah, companion specifications, I think currently like between 50 and 100 of those companion specifications exist. For instance, for packaging machines, for robotics, for injection molding machines, and a lot of other types of machines. Those models are already specified, and many vendors of such machines implement those companion specifications because their customers require it, because it's a standardized interface on how to exchange data with such kind of a machine. And again, here that's a depiction of the value of these companion specifications. You see it has a standardized structure. It has a meaningful name like injection units for injection molding, and screw diameter, and really things that somebody who has knowledge about this type of machine will understand and can deal with it, rather than a standardized OPC UA information model from a PLC where you just have the IEC variables and the IEC types. Okay, that was a very short walkthrough on OPC UA information models. I'm doing this a bit quick now because I see we are already at 45 minutes. A quick overview on configuration of OPC UA TSN networks. It's really comparable to how to configure other industrial field bus technologies. So in your engineering tool, what you do, you describe or you compose your network of devices, you connect them, you configure the devices. Then during the build process, I will rather quickly jump over it. There is a stage where you create OPC UA frames from that information. Then from the OPC UA frames, you create frames on the network. From the frames on the network, you can create the network configuration. And from the frame scheduler and also from the OPC UA frames, you can also create the endpoint configuration. So what frames have to be sent at what time. And for all that information, there are standardized description files. So TSN, for instance, you may recognize this Yang here. Those Yang files are used to describe desired network configuration, and OPC UA has defined a frame format. It's called the nodeset files. And with that two files, you can then configure with standardized clients, you can configure every device in the network. And once they are configured, then usually there will be a topology match and some matching stages in the network before the actual machine then is started. One other thing I would like to make you aware of, also that there are lots and lots and lots of companies who are producing automation devices and that want to have a way on implementing that technology in their devices. And for that purpose, there is an open source project ongoing that deals with implementing or providing open source OPC UA stacks and open source TSN stacks for end stations and also for these bridged end stations, which are the two-port field devices. So if you are interested, or if you want to also make some demos and some analysis, maybe this is an effort that's worth looking into. So I would like to conclude this talk with a few performance examples of real devices that you can reach in such a network, and then give a short outlook also on what B&R is providing on those devices. So the first performance example is a daisy chain network of servo drives. And in this case, it's 100 servo drives connected in a line. Each of them has 3 axes with functional safety. And you see here the communication parameters. It's roughly 100 bytes coming from the PLC to each device and 300 bytes going back. And then also the performance values. And for such a network with OPCOA FX technology, you could run this network with a minimum cycle time of 260 microseconds, which is really amazing compared to today, where we have much smaller networks and also higher cycle times that can only be achieved. Another example is I/O blocks. So here we have 100 I/O blocks, again connected in daisy chain. You see the communication parameters here. It's much less data for the I/O blocks. So it could be digital I/Os, could be analog I/Os. And for such a topology, you would reach a cycle time of 80 microseconds. Here, because we have so little data, actually the forwarding in the individual switches takes more time than the actual frame length on gigabit physics. So here you could take advantage of different topology. So not having one long line, but for instance, dividing this topology into 4 lines with a central switch. And in this case, you can even go down to less than 50 microseconds for 100 of these I/O blocks. So that's really amazing performance for an industrial network. Okay, then very short of the end of the presentation, a short outlook what my company B&R is doing with OPCOA FX and TSN networks. So we have developed one 5-port TSN switch. You can see the features here that we have implemented, and this product is already available. And we also are working on one of such I/O blocks. You see on the left side here, that's the actual I/O blocks. And here on the right side, you can connect the sliced I/Os. And I don't go into detail here, just to say that I/O block, the development is almost finished. So we have prototypes available, and this product will be released in the first half of 2022. Okay, and that concludes my talk. I hope I was able to give you an introduction on what's going on in standardization of industrial communication, industrial real-time communication, and give you a bit of information about the utilized technologies. And if there are any questions or anything you would like to know, please get in touch.
Okay, thank you, Dietmar, for the very interesting talk. So just to remind everybody of the format, if you have any questions you would like to ask, you can put it into the Q&A on WebEx, and I will put it to the speaker. Or if you are still processing the talk and you would like to ask questions later, then I think you can contact the speaker and ask him via email as well. So maybe I can start off with a question. So as I understand from the talk, originally we started off with this very fragmented ecosystem. So industrial communication has this history where everybody has his own proprietary thing. And what we are trying to do here with OPCOA is sort of get a lot of vendors together to offer something similar. So is that now sort of the end of the story, or is it going to be, or is it like a continuous process? Because if you look at how other systems work, everybody is sort of happy maybe for like a year or two, and then one person sort of starts saying, oh, I have a product that's specification compliant, but it's sort of specification compliant plus because we added something to it. And if you now want to talk to my system, you not only have to standard, but also this additional little thing I added on. So is this addressed in this way? Is people allowed to do this or frowned upon, or is it going to be a continual like evolvement of the standard to adopt new things as people move forward?
So actually, you're completely right. It's not the end of the story, but it's the foundation for raising the level of automation in the future. So what we are doing here with this specification is we are providing network infrastructure and we are providing data description. And if you compare with existing field bus systems, you see that there are device profiles. So there is a lot of drive profiles, IO profiles, and so on out there. And the expectation is that in the coming years, also for OPC UA, we will see a lot of that device profiles. And so this is work that is still ahead. And but this is then somehow the end of the story for this communication technology. So the expectation here is that in the future, there will be no more competition on these basic communication features. And the competition between the vendors will be then on other levels. So for instance, on performance features, but also on supply chains and other features, and not on the basic communication anymore.
Okay, so how does this device profile going to work? So is there going to be like a fixed amount, or is it sort of flexibility to say, okay, different people can have different device profile?
There is still flexibility also in these profiles, but the device profiles, they, for instance, define common functionality. So for a servo drive, you have a homing function, you have a function for moving the drive, and you have different types of control in the drive. And those interfaces and those functions, they will be specified. However, on the parameters, not all of those parameters will be specified. There is still flexibility also for different vendors to describe their individual implementation.
Okay, thank you. Does anyone else have any questions for the speaker at this time?
I think I have seen one in the Q&A section.
If there has been one, because I joined late, so I don't think it shows me anything that anyone asked before I joined. So if you see one that I do not see, then please go ahead and answer it.
Okay, I see two questions. The first one is why there is such a large performance difference between OPC UA TSN and Profinet. That's basically because the comparison on this slide was with existing 100 megabit technologies, and also the existing technologies like Profinet. They for 100 megabit you also have larger forwarding times, even for cut-through forwarding, and there's a lot that you can gain by using gigabit physics and efficient cut-through forwarding on gigabit, and also how the frame format looks like on layer 2. For Profinet, the frame format is a bit larger than we have introduced for OPC UA pub-sub traffic. That's how this difference comes along. And also a third aspect is how the cycle is organized in Profinet networks. So for instance, there is a basic multiple that you can only use. So there is a few details. And if you really would like to go into this performance discussion, then I can offer to do this offline, but I can also invite you to have a look at this white paper that's widely available in the internet, to have a look there. Okay, and then we have a second question. What about 2E2 latency when cycles are not synchronized, PLC and network? Unfortunately, I have to say 2E2 latency, I'm not really sure what's meant here. End-to-end latency when cycles are not synchronized. So if you don't have a common time base between the devices, then the question is if you have a need that all frames from all devices reach the PLC in one PLC cycle. So if this is desired, then you need actually a lot of margin in your communication that you can deal with that fading effects. Usually in such kind of systems, for instance, Profinet RT would be such a system where you don't have where you have individual cycle times on the devices, and there it's okay if the PLC does not reach one frame from each device in each cycle. So sometimes it happens that no frame arrives, and in some other cycles it happens that 2 frames arrives. There are lots of applications where this type of behavior is fully okay. Okay, thank you. So that's the questions that I have seen in the Q&A.
Okay, I think at the moment there's no further questions that I see. So thank you very much, Dietmar. Excellent talk. Thank you for addressing the questions. Thank you for the IEEE IoT initiative for putting on the webinar series. To Henry Chang and Karen Miller for helping to organize as well and setting everything up. Thank you for everybody attending on the WebEx and also following on the YouTube. And I hope you can join us for future events as well. Thank you and good night.
Thank you, everybody. Have a nice day.
Thank you. Thank you very much.
All right. Thank you very, very much
Okay.
for putting
Thank
on
you very much.
Everything
Yeah,
went
thank
beautiful.
you. Yeah, very
Okay,
smooth.
we're off YouTube now, right? Okay. Good.
Great.
Okay, thank you.
Okay.
Thank you, everyone.
Right. Have a great day. Thanks again.
Have a great day.
Talk
Bye-bye.
during the
Bye-bye.
Bye.
Bye. Still have 5 participants. Oh, okay.
Okay, I just removed them all. So I think it went well.
Yes.
Everything went really well.
Okay.
Thank you.
Yeah, sure.
So is there anything we need to talk about?
You mean the workflow of the webinar thing?
Yeah, just in general. Anything you need my help with?
Okay. Yeah, for webinar right now, I'm trying to think about the whole logistics. Maybe think about the workflow. Okay, right now, the steps is first of all to invite the speakers, potential speakers, and then get all the information like the bio or whatever. I think it's okay in some sense. The other thing is that for the YouTube thing, I'm not so sure how to promote this way.
You mean
I checked the
before we
maybe
have the webinar?
yes, for example, yeah, before the webinar. I have no idea, but I checked the number of views, and I did see quite a few people will take a look at the